Hi, I'm sorry I can't be there in person with you or even live over Zoom because next week I'm going to be offline. So I'm recording this in advance. So today I'm going to talk about provably beneficial artificial intelligence. So to begin with, let me take you back to the early days of AI. This is Alan Turing, of course. And in 1950, he wrote a very well-known paper, Computing Machinery in the Mind. And that's the paper that introduced what we now call the Turing test. He talked about the possibility of achieving human-level AI. He recommended machine learning as a way to do it. He discussed natural language understanding and planning and all kinds of other things that we now see as an integral part of AI. What fewer people know is that in 1951, he gave a talk on the radio. And as part of that, he was discussing the future. And he said, it seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. So he doesn't offer any solution, any apology, any mitigation, really just resignation. Now, fast forward to the present, we are on the verge. We've been on the verge for a while, but seeing self-driving cars. We've seen computers beat the world champion at Go, something that experts said might take another 100 years. And so some people are saying we are on the verge of achieving our long-term goal in AI of outstripping our feeble powers, as Turing put it. I actually don't think that's true. I think we still have a way to go. Here's a commentary from Francois Chollet, who is the author of one of the well-known deep learning packages and a very good textbook. And in the final chapter of the textbook, he says many more applications are completely out of reach for current deep learning techniques, even given vast amounts of human annotated data. He goes on to say that the main directions in which I see promise are models closer to general purpose computer programs, which is very different from training deep networks, which are really circuits. And so I actually agree with this. And in fact, I and many other people have been working on that for nearly 3 decades now. And the field that we developed is called probabilistic programming. We produce things called probabilistic programming languages, or PPLs, which are fully Turing expressive ways of writing down probability models associated with completely general inference algorithms, so that you can answer any query with respect to any data and any prior knowledge expressed as a model in the PPL. And this field is growing exponentially, as you can see. By 2019, already 2,000 papers published per year on PPLs. So I do think that the pendulum is going to swing back towards these more symbolic, structured, declarative, analytically rigorous representations. And then in combination with deep learning, we'll see maybe the next stage of progress in AI. But I think it's prudent to assume that AI will achieve its goal. We will eventually build AI systems that make better decisions than humans, not just on the Go board or at the wheel of a car, but in general in the real world. No matter what the decision circumstance, AI systems will have far more knowledge to draw on than any human being can ever acquire in a lifetime. And they will have far vaster computational capabilities. The alternative, of course, is to assume that actually, no, AI is just going to run out of steam, and we won't ever achieve our goal. And that's a little bit like driving a bus towards a cliff, with the whole human race as passengers and saying, don't worry, we are guaranteed to run out of gas before we get to the edge of the cliff. And I don't think that's a good way to manage the affairs of the human race. So I think we have to take this possibility seriously, and we have to say, maybe Turing had a point, right? If we're going to build entities that are more powerful than us because they can make better decisions, which means that they will get what they want. How do we retain control over more powerful entities than us forever? And obviously, Turing saw no solution to that problem. So I actually would like to find a solution to that problem. And if you're interested in some of the arguments as to why we should take this problem seriously, there's a paper in IEEE Spectrum from October 2019. I have to say that because it's in the Spectrum, the author doesn't get to choose the title, so the title is a bit rude, but I think that is a fairly accurate gist of the paper. So to understand where things go wrong, I think it helps to understand the standard model for artificial intelligence. And this standard model goes back a long time, and it basically looks like this. You have a person on the left, and the person states the objective. Here I'm writing down the standard objective for a reinforcement learning system or a system that solves the Markov decision process. But it could be a logical goal if you were talking to a planning system. It could be various other kinds of information about what it is that you want. But the idea is the human states the objective and the machine figures out how to optimize that objective. And this is not actually restricted to AI. It's the way we do things in control theory. Typically, you minimize a cost function. In statistics, you minimize a loss function. Operations research, as in the example, maximizes a discounted sum of rewards. Economics maximizes a utility function or a social welfare function, and so on. And it's also the case that we need not transmit the objective to the AI system. We can simply build AI systems that by design optimize the objectives. So for example, if you look at a self-driving car, the human does transmit the objective of, I want to be at the airport. But the part of the objective that says it's really bad to run over pedestrians is more built into the algorithms of the car. It doesn't have to be told that. It just has algorithms that won't let it run over pedestrians. So it's compiled away and built into the control algorithm of the vehicle. We also should not think necessarily of a single robot the way I've shown it here. The thing that's maximizing the objective could be an entire distributed system. So if one day all the Uber drivers are robots, then it might be the entire Uber network that is optimizing some objective that the Uber corporation would like its network to optimize. And the problem with this approach is something we've known for thousands of years. And I call it the King Midas problem, because King Midas specified the objective, namely everything I touch should turn to gold. And he got exactly what he wanted. The gods optimized that objective for him. And then, of course, his food and his drink and his family all turn to gold, and he dies in misery and starvation. And many, many cultures have this the same kind of legend. And if you get 3 wishes, your third wish is probably going to be, please undo the first 2 wishes because I've made a mess of the universe. So I think that what Turing is imagining is that when machines are more powerful than us and they're pursuing incorrectly specified objectives, they will succeed in getting those objectives, and we won't get our objectives anymore. And we may have no opportunity to interfere. and we may no longer exist as a byproduct of optimizing this incorrectly specified objective. So with this standard model, which, as I said, is very widespread and has been pretty successful up to now, in the long run, the smarter the AI system, the worse the outcome is going to be, the more difficult it's going to be for us to interfere, and the more of a mess the AI system is going to make of the rest of the world while it's optimizing this incorrectly specified objective. And I believe we're starting to see some of the consequences of this. Other commentators say, well, of course we're seeing the consequences of this. There are already super intelligent machines that are already destroying the world, and they're called corporations. For example, fossil fuel corporations have been executing a 50-year very clever political and public relations and disinformation campaign to allow them to continue to destroy the climate of the Earth while generating profits. And the human race has lost. And basically that's it. So that's one argument. But I think even simple machine learning algorithms operating in social media are presenting a similar kind of threat. So what an algorithm does, a content selection or a recommender algorithm in social media, is it chooses what to present to the user, what they should read next if it's on YouTube, what video is going to get loaded next. And in many ways, these algorithms have more control over human cognitive input than any dictator has ever had in human history. Now, I don't want to say that they are, sinister, evil dictators who designed these algorithms. I think possibly what the social media platforms thought was that the way the algorithms would work is to learn what people want and stop sending them stuff they're not interested in, that they don't click on. And the algorithm, that's how the algorithm will optimize its objective, which is specified to be click-through, the probability that you click on the presented item. Sometimes it's engagement, how long are you engaged with the platform, and so on. But in fact, the way the algorithms work, and this could also be the algorithms combined with the A/B testing done by the marketing department, is that they modify people to be more predictable. And this is a natural consequence if these are reinforcement learning algorithms. That's what they do. They want to maximize not the probability you're going to click on this item, but the total amount of clicks they're going to get over future history. And they're going to get many more clicks if they can change you into somebody who's more predictable so that they can feed you exactly the stuff that they know you're going to click on. And maybe that means they turn you into an eco-terrorist or a neo-fascist or whatever, so that you then get to consume all the red meat that whole industries are springing up to produce. And actually, if you look at the new EU AI regulations, they do, not so explicitly, but they do actually say, because Article 3 of the EU Charter of Human Rights says that people have a right to mental integrity, and the general EU AI regulations say that an AI system is high risk if it can impinge on fundamental rights, which include the right to mental integrity. Then there's, I think, an arguable case that's reinforcement learning algorithms that are inevitably, mathematically going to manipulate people to change them psychologically into a different kind of person, that those algorithms are impinging on fundamental rights. So how do we get into this mess? How do we develop a standard model, a widespread methodology, and one that I actually, laid out to some extent in my AI textbook, when successful pursuit of that standard methodology could potentially lead the human race into serious trouble? And I think it came about because in the early days of AI, we were looking for a way to turn this dream of artificial intelligence into a kind of a well-defined discipline where we could actually state what it was that we wanted our algorithms to do, and we could measure progress and derive algorithms from the definition of what we were trying to do. And to do that, I think the early researchers borrowed a pretty, by that time, well-accepted notion of intelligence as applied to humans. And this is the notion we sometimes call rationality. But in a single sentence, we might say that humans are intelligent to the extent that our actions can be expected to achieve our objectives. And then the natural thing is to just transliterate that definition to machines. So machines are intelligent to the extent that their actions can be expected to achieve their objectives. And that's the standard model that I just showed you, where the human supplies the objective. But now we want machines that achieve the objectives that we supply. And that probably seemed pretty reasonable at the time, but I think, I think this is what Turing was worried about. And the King Midas problem suggests that this is really not a good idea. So what we want instead, I would argue, is not just this sort of pure undirected intelligence as the general capability to optimize any stated objective, but actually we want machines that are beneficial to human beings. So machines are beneficial to the extent that their actions can be expected to achieve our objectives. And so that's a different problem, and it's obviously a more difficult problem because the objectives are in us and not explicitly in the machines. And you might wonder, well, how on earth is it going to satisfy this property of being beneficial? But we'll see that, in fact, this is possible. And it actually leads to, I would argue, a much more interesting kind of AI that exhibits behaviors that the standard model can't really produce. So if we have to, I suppose, in homage to Dr. Asimov, if we have to write down 3 principles, I think I'd write them down like this. So first of all, the robot's goal, its purpose in life, is to satisfy human preferences. And I'm using the word preference here in the same sense as von Neumann and Morgenstern and other people who developed the basic theory, mathematical theory of rationality in the middle of the 20th century. So this means preferences not just over what kind of pizza you like, but preferences over entire futures, in fact, over entire probability distributions over entire futures. So the objects between which preferences exist are very, very complex objects. But that is really what it means, right? It's what kind of future do you want? And the robot would like to bring about the futures that you would like to bring about. But the key point, the second principle, is that the robot does not know what those preferences are. It has uncertainty, and this uncertainty is what's going to protect us. And it's going to make the robot behave in ways that a robot that has certainty will never exhibit. The third principle is basically, how does the robot acquire any information about human preferences? How do we ground this notion of human preferences from the point of view of the robot? And the answer is that, absent some mind-reading technology or some fancy fMRI, the evidence of preferences that a machine can have comes from human behavior, human choice behavior, everything that a human being does, including here verbal behavior, like asking for a cup of tea. That's evidence about human preferences. And I put an asterisk on the word evidence here because it's complicated evidence. And it's complicated because humans are not perfectly rational entities. Our actual choice behavior does not perfectly reflect our true underlying preferences. And you can tell because we often do things that we regret. You can tell because chess players and Go players play losing moves, even though they obviously want to win. But if we understand enough about human cognition, then we can interpret the evidence from human behavior, including the entire historical record and all the rest, to learn more about human preferences. So those are sort of principles that I want AI researchers to understand. They're not laws in the way that Asimov thought about writing down that robots sort of have to follow. But they're sort of guidelines for AI researchers developing AI systems. And from these three principles, we can actually formulate a mathematical problem that we want the machine to solve. It's called an assistance game. It's a game because it intrinsically involves not just the machine, but also the human, because of this flow of preference information from humans to machines. And it's called an assistance game because it's specifically constructed so that the machine is sort of constitutionally going to be of assistance to the human. And in these assistance games, basically, the better we make the AI system, the better the outcome is going to be, because first of all, the machine is going to be better at learning about our preferences and interpreting our behavior, including verbal behavior, as evidence of preferences, but also better able to carry out plans that will actually be beneficial to us. So very briefly then, an assistance game, the simplest kind, involves one person, one machine. And the person has some preferences, and we typically use the Greek letter theta to represent generally what the human's preferences might be. And we assume that there's some connection, that the human is going to act roughly according to those preferences. Doesn't have to be perfect, but there has to be some connection between the two. And then the machine, as the principle 1 states, the machine has to maximize theta to come up with the actions that in expectation give the best possible outcomes according to human preferences. But the machine doesn't know what these preferences theta are. And in this is the Bayesian formulation, it will have some prior probability distribution, a prior belief about human preferences. It could be extremely vacuous, or it might be quite knowledgeable. And then the interaction is going to unfold, and the machine has to basically design its behavior, which is also contingent on what the human being does, and vice versa. They have to design their behaviors in such a way that in the end, we get the best possible outcome for the human. And this is developed in a whole sequence of papers, which are listed at the bottom. And what we find when we solve these games, so you set the game up, and then you just solve it. You say, okay, what is the way that the machine is going to behave if it solves this game? What is the human going to do? We find that, as one might expect, the human has an incentive to teach the robot. So the human will carry out behaviors that the robot interprets as conveying information efficiently about human preferences. And then the robot, because the robot is solving the same game, except from the robot's point of view, the robot is able to understand the human teaching behavior as conveying this information. Sometimes the robot will ask questions. Sometimes it will, if it devises a plan and it's not sure that the plan is consistent with human preferences, it might ask permission or offer two plans and say which one would be better. It will generally defer to the human, because a human instruction, like saying stop, is conveying very strong preference information that whatever the robot was doing or was about to do is undesirable. And very importantly, robots that are solving these assistance games will allow themselves to be switched off. And this is really the core of the control problem. And in fact, in another lecture, Turing wondered whether it might be possible to switch off the machine. And he said, even if we could, the human species would be greatly humbled. So we'll see in a minute exactly why participants in assistance games, the robot participant, will allow itself to be switched off. So we call this the Offswitch problem. And just to illustrate it, here's our robot, this big, heavy 400-pound PR2 robot that we have in the lab. His name is Brett, the Berkeley robot for the elimination of tedious tasks. And like all of these kinds of robots, it's legally required to have an off switch on the back. And there it is. And so the problem, why it's a problem, is that in the standard model, the robot will tend to disable its own off switch, right? So if you give the robot some fixed objective, like fetch the coffee, if it has two brain cells to rub together, it's going to say, okay, you can't fetch the coffee if you're dead. And so I need to make sure that nobody presses my off switch. And therefore I have to disable it or put some other defensive mechanism around it, or even sort of preemptively disable the humans who might press the off switch. And so this is exactly the kind of behavior we would like to avoid. But in the classical standard model for AI, it's really unavoidable. And it's not because we're building in self-preservation. It's because we gave the machine an objective. And it's going to take preemptive steps to protect itself in order to make sure that the objective is achieved. But what I'll show is, in fact, that when the robot is uncertain about human preferences, about what the objective is it's supposed to be carrying out, then typically it won't disable the off switch. And we can see it. I'm going to give now a sort of a very, very simple mathematically described example where the robot essentially has two choices. So it could switch itself off, commit suicide. So that's the right branch, and we'll say that that's of utility 0 to the human. So here we're talking about the utility function of the human. How desirable is it for the person? And this is one way of expressing preferences. The other action that the robot could do is to push the big red button, right? And maybe the robot's not sure what the big red button does or how happy we would be for the button to be pressed. Perhaps it, starts all the sprinklers in the building. Perhaps it sets off the fire alarm. Perhaps it starts a nuclear war. But at the moment, the machine's prior says that the value of the action is uncertain. So here I'm showing a probability distribution with most of the probability mass in the positive quadrant, meaning that on the whole, the machine expects that we're probably going to be happy with the outcome of this big red button. But there is a significant possibility of a big downside. That's the left quadrant. Now, we're going to give the robot another option, right? Which is to wait and let the human do something, right? Now, if the robot decides not to wait and decides actually just to go ahead and push the big red button, that's the equivalent of disabling the off switch. So it's preventing the human from intervening and perhaps switching the robot off. So if the robot's waiting, that's the equivalent of not disabling the off switch, so allowing the human to switch the robot off. So there's the human choice to switch the robot off. And of course, that has, as before, the utility of 0 for the human. And you might say, well, what's the point? The robot can do that for itself. So if it was a good idea for the robot to do it, then what's the point of waiting and letting the human do it? And the answer is that actually what waiting does is it gives the human a choice the human doesn't have to switch the robot off. The human could allow the machine to go ahead. And of course, if the human does allow the machine to go ahead, it's because pushing the big red button is in fact desirable. So now the left quadrant, the negative outcomes for the big red button have gone. And in expectation, the robot is now sure that pushing the big red button is a good idea and can go ahead and do that. And so you can calculate the value to the robot, which is also the value to the human, because the robot only cares about human preferences, the value to the robot of choosing wait over committing suicide with pressing its own off switch or pushing the big red button. And you can show that waiting is always a good idea when the robot has uncertainty about human preferences. So it's that uncertainty that gives the robot a positive incentive to allow itself to be switched off. And why is that? Because giving that human a choice provides an opportunity for the machine to learn something about human preferences and therefore make a better decision. And we can show under certain assumptions of matching the robots prior to the human's own uncertainty that the robot is, from the point of view of the human, is provably beneficial in expectation. So the human is provably better off with this type of robot than without. So this is obviously a very, very, very simplified depiction, but I believe that all the elaborations that we've examined, the core insight is preserved, that it's uncertainty about human preferences that allows the human to have control over the robot. And when the uncertainty goes away, human control also goes away. So I would argue that, in fact, we need to basically rewrite the entire AI textbook because every area of AI assumes a perfectly known objective. In the symbolic logical part of AI, in search, constraint satisfaction, planning, it's expressed as logical goals or logical constraints. In Markov decision processes, it's expressed as a reward function, same in reinforcement learning, and so on. And every one of the core technical chapters of the AI textbook begins by saying, how do we formulate these search problems or planning problems or reinforcement learning problems? And they all assume that we're able to specify the reward or the goal or the cost function correctly. And that assumption, I'm arguing, is both false and extremely dangerous. And we should instead study how to do these things in terms of algorithms, interaction protocols between humans and machines in such a way that allows for uncertainty in the objective and some flow of information at runtime about human preferences to the algorithm. So that's a lot of work, and I'm looking forward to doing that. I'm not looking forward to rewriting every chapter of the textbook. But let me just give a few simple examples. So one is just supervised learning, right? Which is the branch of machine learning where you're given lots of examples, for example, photographs of objects, and you're given labels, correct labels for all of the training data. So each photo is labeled with, giraffe or school bus or ostrich. And then you're trying to learn to predict and classify new images that you haven't seen before. And this is one of the areas where deep learning has made significant contribution to the capabilities of AI systems. So the way that's set up as an optimization problem is that you specify a loss function, which basically says how much does it cost to misclassify an object of type A as an object of type B. And then you minimize that loss function on the training set by adjusting the prediction function, in this case, a neural network. You adjust all the weights of the neural network to try to minimize that loss function. And in fact, usually people kind of skip over the step of specifying this loss function because, for example, in the ImageNet database, there are 20,000 categories. And so there are 400 million different misclassification errors. And no one has ever written down the cost of each of those misclassification errors. And typically, people just ignore it altogether and they don't write down the loss function. And so their algorithm is effectively minimizing a uniform loss matrix where every error is considered to be equally bad. And then what happens, as happened with the Google photo service, is that you accidentally classify a human being as a gorilla, and you upset a lot of people, justifiably, and you have a public relations disaster on your hand because that type of error is extremely costly. Whereas misclassifying one type of Norfolk, say a Norfolk Terrier as a Norwich Terrier, or vice versa, I don't even think the terriers care about that. What you need to do instead is actually say, well, this 400 million entry loss matrix, I don't know what it is. I, the algorithm, have uncertainty over what the loss matrix is. And we don't actually have, at least until very, very recently, machine learning algorithms that can handle uncertainty over loss matrices. And you should see or expect very different behavior from such algorithms. For example, the algorithm should be entitled to say, I don't know what this thing is because it's quite risky since I don't really know the loss very well. It's too risky for me to make a classification because I don't know where the boundary should be. Interestingly, you can't get the loss information from classification decisions that humans can make perfectly. So if every photo is completely unambiguous, you don't learn anything because the human is taking no risk in assigning a given label to the photograph. Whereas if your photographs are extremely blurry, low resolution, poor lighting, and it's quite difficult to tell which is which, then from the human decisions, you can actually infer information about the loss matrix. And so there are a couple of recent papers that study this problem, one by my student Cassidy Laidlaw, another one by a student of Anka Dragan, Kush Bhatia. So just thinking about supervised learning and adding this notion of uncertainty about preferences gives you a whole new interesting research agenda to explore. Another interesting thing is to just go back and revisit this standard notion of giving a goal to a machine, right? And every AI lab that gets a mobile robot typically will figure out how to program it to fetch the coffee. And then whenever you want a coffee, you say fetch some coffee and off it goes. But what does this really mean? Does fetch some coffee really mean that the robot's only objective, its only information about human preferences is that having coffee is the only thing that matters? And I would argue that classically, yes, that's what it has meant. And maybe they might throw in, get it quickly rather than slowly. So you put in some cost of time. But that's only because the robots can't really do very much and they don't present much of a threat. But really, there's a lot more that you care about. For example, you don't want your robot to mow down the other people in Starbucks to get the coffee quicker, which it would do if you said the only things that matter are me getting coffee and getting it quickly. In fact, what fetch some coffee means is probably I'd like some coffee, but actually that's all it means. It doesn't tell you that nothing else matters. If this is all you know, then you have massive uncertainty about the rest of the human preference function. And in that case, with this massive uncertainty, what is the robot to do, right? So one answer actually comes from a paper, quite an old paper from the 1990s by Mike Wellman and John Doyle, where they introduced this notion of goals as ceteris paribus preferences. Ceteris paribus meaning all other things being equal. So when someone says, fetch me some coffee, what they mean is that me having coffee is preferred to me not having coffee, all other things being equal, right? So that doesn't say nothing else matters. What it does say is that if you can get me the coffee without changing anything else, then I'm going to be happy. If you're going to change other stuff, then you need to know more about my preferences to know whether that's okay. So this leads then to minimally invasive behavior, that the robot is going to avoid messing with any attributes when the value of those attributes or the preference ordering over the values of those attributes is uncertain. And in the extreme case, interestingly, even if the machine has no information whatsoever about human preferences, it can still be useful to us. And how is that? By taking actions whose only effect is to expand the set of options available to the human, right? So one example might be if I've forgotten my password, the robot could tell me my password. That now gives me a whole bunch of options I didn't have before. And the robot's basically just assuming that I'm going to use that additional freedom in some way that's beneficial to me, or I'm not going to use it at all, which is fine. And so this notion of empowering is something that sort of falls out as the kind of the null case, right? Even in complete absence of preference information, the robot is still going to try to empower you. And so it's always going to try to empower you, actually, even given more information about preferences. Another interesting observation about this case is that it's possible to infer things about human preferences, not by observing any human actions directly, but simply by looking at the state of the world, right? And this might appear to violate, if you know about the naturalistic fallacy, it says that you can't, this was actually formulated back when people made more religious arguments for moral rules, that the naturalistic fallacy was trying to infer God's will from observation of the natural world, or trying to infer moral truths from the way the world is. And that was usually seen to be a fallacy. But in fact, here, what we're saying is, when you look at the state of the world, it's not a state of nature. It's actually the result of the behavior over thousands of years of these quasi-rational agents called humans. And so, so by observing the state of the world, you can actually sort of work back and say, what is it that these humans must like for them to have produced a world that looks like this? And then, so you can infer a lot about what they like. You can also infer a lot about how stupid we are, which is a separate question. So now I'm just going to quickly go through some of the interesting research questions that come up as we start to unroll this very, very broad research agenda. So one set of questions comes up mainly to do with the third principle about inferring preferences from behavior. And as I mentioned earlier, this is going to work only if we have some notion of the process, right? We're going to reverse engineer human cognitive architecture, so to speak. So we have to have some notion of the process by which the behavior is produced from the preferences. And so we have to deal with, as I said, the fact that a chess player or a Go player is computationally limited. They make losing moves, even though they want to win. So if we see them make a losing move, we shouldn't infer that they want to lose. We should understand that they have certain kinds of computational limitations, unless they really seem to be throwing the game away. Another important fact about human behavior is that it's hierarchically structured. We're not taking the first best action for the rest of our lives. We're actually always engaged in a very deeply nested set of commitments. For example, I assume that you're participating in the International Conference on AI and Law and listening to this talk, sitting politely, reading your email while my voice is droning in the background. But you're not getting up and dancing on the table or swimming in the ocean, or all kinds of other things you could do. And that's because you've committed to some small world, right? By making a higher level choice, you now have a small set of lower level choices about how to implement that. And this is absolutely ubiquitous in human behavior. And really, we can't understand what people are doing or why, what their preferences are, unless we have some notion of this set of activities and the structure that people are engaged in. I just want to mention one more of these. They're all very interesting, and each one could be an hour-long talk. But plasticity of preferences is really important. And this is the one aspect that probably is, in the end, going to lead to a revision of the three principles, because the three principles, and in fact, the general notions of rationality, actually rely on the idea that there are such things as stable preferences. And if people's preferences are plastic, then one thing the AI system could do would be to actually modify those preferences to be easier to satisfy. And to some extent, that's maybe what the social media algorithms are doing. And that causes all kinds of, obviously, practical problems you want to avoid. But also, there's just a difficult philosophical question that if our preferences can change, do I, and if I'm going to take an action that is going to affect you tomorrow, do I take the action that you prefer me to take today that's going to affect you tomorrow? Or do I take the action that you're going to prefer tomorrow that I take tomorrow? In other words, which of the two humans, you today or you tomorrow, do I satisfy? And this is not a question that has an obvious answer. Another set of questions obviously comes up. I'm sure many of you are thinking through some of these questions already, particularly if you have training in jurisprudence or political theory, about decision-making on behalf of many humans. So among the simpler problems are the fact that people had many different preferences. And I want to be absolutely clear here. I'm not proposing that the system learn, the AI system learn one sort of value system, one set of preferences. There is no, human preference in general. Really, we're talking about learning 8 billion individual preference models. And the machine has no preferences of its own. It doesn't have any values, if you want to think of it that way. So that's relative. That part of it is relatively easy. The difficult part, of course, is now you're going to make a decision. How do you trade off the preferences of all those individuals? It may, your decision may affect thousands or millions of people. And just like governments or autocrats, you have a problem in deciding what is the right thing to do when people's preferences, some people may be less happy than others about any particular decision. I do want to mention interpersonal comparisons of preferences, because this is raised often as an obstacle to any attempt to trade off the preferences of one individual for another. And in fact, if you read Ken Arrow's papers that introduce his famous impossibility theorems, he states as an axiom pretty much that any comparison of preferences between individuals is meaningless. And therefore, any form of trade-off simply can never be justified. And so that means that if you had to make Jeff Bezos wait 1 microsecond longer for his private jet to arrive in order to save the life of a starving woman whose child hasn't eaten for months and months, sorry, you can't do that. Because these are not comparable preferences. There is no common currency between the two, and you can't say that one is bigger or more important than the other. So I don't believe that. I don't believe anyone actually believes that. But nonetheless, there's a significant strand of thought within economics that takes that claim as axiomatic. So let me talk about aggregation over individuals, because this is in some sense, the core problem that social scientists have studied for thousands of years. And then I'll mention some more sort of individualized aspects of decision-making on behalf of multiple people. So one of the people who developed utilitarianism into an axiomatic theory is John Hassani, who won the Nobel Prize, died, I think, in 2002, was a professor at Berkeley. And he proved a very famous aggregation theorem, which says that under certain fairly simple axiomatic assumptions, similar to von Neumann's axioms of rationality, with a couple added to deal with the fact that now we're talking about many people. Hassani shows that every Pareto optimal policy, which means that every policy you could have on behalf of multiple people that isn't strictly dominated or weakly dominated by some other policy. So every sort of at least admissible policy optimizes some linear combination of the preferences of the individuals. And then he argues that, you know, by symmetry and fairness, we should simply use equal weights for the preferences of each person in this linear combination. And this is where, of course, the interpersonal comparison issue comes up. But his theorem assumes a common prior over the future, meaning that every one of the people has to have the same beliefs about how the actions of the robot are going to unfold and affect the future. So this common prior assumption, as you can imagine, is a bit hard to satisfy in real life. And we showed that when there isn't a common prior, when people have different beliefs about the future, actually the theorem changes its nature quite considerably. It still obviously has Hassani's theorem as a special case, but the general case, it doesn't look like what you might expect. What it says is that all Pareto optimal policies weight the preferences of individuals according to how well their prior belief turns out to fit with reality. Right? So the likelihood of the subsequent observations according to that person's prior determines the weight that their preferences are going to have in any Pareto optimal policy. And that could be, you know, typically it's going to be, they're going to be exponentially large differences between the weights assigned to different individuals. So it's sort of extremely unfair sounding. But why is this? Well, to explain it very simply, everyone prefers these policies because everyone, by definition, believes their own beliefs. And so they believe they are going to be the ones who win out and not the other people. And so, in fact, they insist on these policies. And everyone insists on them. And so that's why they're Pareto optimal. So we've yet to work out really the sort of social, political, moral consequences of this, but it is a theorem, and we have to accommodate it somehow in our understanding. So let me close up just by talking a little bit about altruism, indifference, and sadism. So to think about these things, what economists often do is to divide the utility that a person has for a given future into two parts. The self-regarding part, we might call that sort of intrinsic well-being, which would refer to, you know, do I have enough food? Do I have enough warm clothing? Do I have a safe place to live? You know, do I have health? Do I have mental integrity? And so on. So the things about myself that I might care about. And then the other regarding part, like, you know, what about the rest of my family? What about my neighbors? What about my conspecifics, right? Or all the other humans? And what about their well-being and how much weight do I assign to that? And usually these theories just sort of, you know, add these together. There's actually no reason why you have to use addition. And in fact, you might want to look at not just adding them as independent contributions, but you might care about the entire distribution. So it's sort of more like a joint distribution over well-beings. But I'm going to just look at this in this very simple model with two people, Alice and Bob. And so I'm sorry for the equations, but they're very easy, right? So Alice's utility, U sub A, is Alice's well-being. That's her sort of intrinsic stuff, that just the self-regarding part of the utility function. And then this is Bob's well-being. And then this is the caring factor, right? How much does Alice care about Bob? Okay. And so if Alice cares about Bob and Bob has lots of well-being, then Alice has higher utility. Alice is happy. And similarly, Bob has his own well-being, and then Bob cares about Alice and Alice's well-being. Okay. So obviously this is a gross oversimplification of reality, but it actually serves to illustrate some important points. So the first obvious thing is that the caring factor, the sign of the caring factor, makes all the difference, right? If the caring factors are positive, then these people have some degree of altruism. If the caring factor is 0, then they're completely indifferent. It's not that they want to hurt the other people, they just don't care whether the other people live or die. And if you find that kind of bizarre, think about how much you care about the well-being of people on the 3 planets furthest from us in the galaxy, right? At least the 3 inhabited planets furthest from us in the galaxy. I bet you don't care very much, right? So it is possible for us to be indifferent. And then sadism would mean that this coefficient C is actually negative, which means that you literally benefit from the suffering of others, right? And you're willing to inflict suffering, even if it costs you something. So not stealing from people, right? That's inflicting suffering on them, but to gain something for you. And so that can happen even if you do care about them. But if the caring factor is negative, then you really are what Harsanyi in fact calls a sadist. And so Harsanyi says, absolutely, we should not count these negative caring factors, right? And he says, no amount of goodwill to individual X can impose the moral obligation on me to help him in hurting a third person individual Y. So the recommendation here is, yes, we'll do this aggregative utilitarianism, but we will zero out the sadistic factors, the sadistic preferences of individuals. And most people seem to agree that this is a perfectly reasonable thing. But in fact, when you work through it, it turns out that there's actually more you need to do, and it becomes more problematic. And that's because an important part of human utility is relative well-being. So not just how nice is my house, but is my house nicer than everybody else's? Or is my car the newest and shiniest? Or do I have a Nobel Prize, right? What is the value of a Nobel Prize? It's not just that you get €1 million or 8 million kroner or whatever it is. It's that other people don't have one. It would be much less valuable to you if everybody had a Nobel Prize, right? And so this has been known for a long time. Even in the 19th century, Veblen talked about it, and economists now call these positional goods, right? Because it's to do with not just the absolute properties, but the ranking of these goods relative to others. And this is a really important part of self-esteem, of tribal identity, why people care so much about the success of their baseball team or their football team or whatever. And if you write this down, right, you can put pride and envy into this same simple kind of formulation. So here's Alice's utility again, and Alice's well-being. Alice's caring factor, this is sort of the altruist factor. And then this is the envy part. So if Bob has higher well-being than Alice, then to the extent that Bob has higher well-being than Alice, Alice experiences envy. So we have a positive envy coefficient, and then that results in a negative term because it makes Alice less happy, right? So the better off Bob is, the more envy Alice experiences. And similarly, if Alice's well-being is bigger than Bob's, then Alice feels pride. And so the pride coefficient is positive, and that contributes to Alice's feeling overall happiness. And again, these are very, very, very simplified, but the point here is that if you just rearrange the equation and look at Alice's attitude to Bob's well-being, you see that the envy and pride coefficients, these are negative coefficients on Bob's well-being, just like sadism, right? And that's because Alice feels more pride and feels less envy when Bob is worse off. And so in those regards, we might say, well, maybe we should zero out the pride and envy coefficients as well, because they work just like sadism. They result in this sort of zero-sum competition, the keeping up with the Joneses, all kinds of conspicuous consumption, et cetera, et cetera. A lot of evils of modern society come from these. So, but zeroing them out, right, because they are so big, they feature, might think sadism is fairly rare and unusual, and maybe people could learn not to get their jollies that way. But these positional goods, these relative preferences, are massively important in people's self-conception and how our whole world works. So we should be very careful before we zero them out. So if you're interested in these things, the book Human Compatible explains them as best I could for a non-technical audience. There are a bit more technical stuff in the footnotes at the end and the appendices. And then the 4th edition of the AI textbook has some stuff, some of the examples I showed, and more mathematical analysis and theorems and technical explanation of the ideas are in there. So to summarize, I've argued that the standard model for AI leads to this loss of human control, and we actually need to fix it. And unlike Turing, I believe it's possible. And it's through this idea of making these provably beneficial AI systems that are uncertain about human preferences that they're supposed to satisfy. And I would argue that these type of AI systems are just better, right? These are the ones we want, right? These are the household robots that actually adapt to our preferences and behave in ways that are minimally invasive and ask permission, and they defer and so on. They do what we want a good household robot to help us with. So I would argue that we should stop thinking about the sort of two separate fields, one being AI and the other one being AI safety or AI ethics, where we sort of wag our fingers at the AI people and say, bad, bad, bad. That doesn't work, right? The only way this is going to work is if every AI researcher in the world, gets up in the morning and it's fine if some of them say, okay, I need to save the world from AI, but what we really want, what we can only expect them to do is to get up in the morning and say, I'm going to do some good AI today, right? Just in the same way that, a bridge designer gets up and says, I'm going to build a, really good bridge today. We don't have to constantly remind bridge designers that the bridge is not supposed to fall down. But at the moment, we constantly have to remind AI researchers that the AI system is not supposed to take actions that are harmful to human beings. And so it has to become intrinsic to what it means to be doing AI well, to be a successful practitioner in your field, that you take into account these considerations in how you design AI systems. I should mention a couple of other really important problems. So on the side of regulation, how do we ensure that people are going to use the provably beneficial AI system design templates and not bypass it? And that's a really tough problem in itself. And if you think cybercrime, which is running at $1 trillion a year, if you think cybercrime is a problem, this is going to be way worse. And on the flip side, we also have to be very careful about overuse, right? And this is a picture from Wall-E where human beings have turned over the running of civilization to machines. And in the process, they have infantilized themselves. They've enfeebled themselves. They can no longer understand how their own civilization works. They can no longer take meaningful action. And that's also an extremely dangerous and unpleasant and possibly disastrous, because it's so fragile, a future that we want to avoid. And this is more of a, I would say, a cultural than a technical problem. The AI systems might well, if we design them well, right, because autonomy and civilizational vigor is really important to us, the AI systems may say, okay, I don't think I should do everything for you. And at some point, you're going to have to tie your own shoelaces. But we will tend always to err on the side of putting that off into the future and saying, oh, I really want you to tie my shoelaces today. And that's a slippery slope. So we don't have good solutions for those problems. And on that note, I'll say thank you very much for your attention. And once again, I'm sorry that I couldn't be doing this live with you next week.